Okay, cool. So how today's class is going to work is I didn't get to finish everything I wanted to do on Wednesday, mainly the last part of propositional logic. So what we'll do is I'll go over that maybe for the first 20 minutes or so. Oops, okay. Yeah, go over that for the first 20 minutes or so. We'll break, you'll do attendance, and then we'll go into discussion. So how discussion will probably work after reading your feedback from discussion last week is it'll be more guerrilla section style. So we'll give you all time to discuss the problems, and then we'll sort of just take it up. It'll save time that way, and we'll also be able to collect student input. Okay? A couple other reminders. So one, office hours are official. There's Tuesday 2 to 3 and Thursday 5 to 6, both in Corey 299. So feel free to come to those. Corey 299 is kind of this hidden room in Corey, like near the elevators at the back of the building. Just a reminder that our midterm date has been moved up from October 17th. Now it's October 10th. It's 3 weeks from this Wednesday. In Berkeley time, I guess that's still a long time away, so don't worry about that now. Homework 1 grades are out. So did everyone check Gradescope to see what their homework 1 grade was? Okay, sounds good. And homework 2 was just due. I extended the deadline slightly till 7, but normally that won't happen, so it's essentially due now. How we graded homework 1 was we gave you a 5 if it seemed like you made a reasonable attempt and showed a decent amount of work for most, if not all, of the problems. It was a 2 if it looked like you didn't attempt all of the problems, or the problems you did attempt, you didn't show very much work, and a 0 if you didn't submit it, essentially. And so if you have any feedback on that system, feel free to let us know. This is the first time we're doing this, but we will probably use that system in the future. Okay? Additionally, for lecture videos, my original plan was to sort of record them beforehand and then come to lecture, but like that takes a lot of time. I like watching TV. So instead what we're going to do is I'm going to webcast the live lectures right now. So I'm recording this right now, and then I can post it immediately after. So we'll still have the videos. They just won't be pre-recorded. They'll be recorded live. Okay? Any questions with any of the announcements or what's going on today? Yes?
The last homework had questions from topics we haven't covered.
Yeah. So again, the idea was that you sort of attempt them, read the textbook, but we'll discuss a lot of those questions today. So don't worry if you weren't able to get a lot of those things, right? We'll take those into account when we're grading the homework. Okay, the idea is to give you exposure that will either come from lecture or discussion or doing the homework. Anything else? Okay, so let's get into it. So we're going over the latter half of propositional logic. Just to recap from what we covered last Wednesday, we said that a proposition is a statement that has a definitive value, okay? It's either true or it's false, okay? And it doesn't depend on anyone's opinion. It is factually either true or false, okay? And you might have seen in the homework, in the textbook, or even last week in lecture, P at X usually represents a proposition that depends on a variable X, okay? So given some variable X, P of X is either true or it is false. Any questions with the definition of a proposition? Cool. And we also went over 3 logical operators, right? So we went over the conjunction that reads A and B, and its parallel in set theory was the intersection, right? So we said the intersection of 2 sets A and B was a set of all elements X such that X is in A and X is in B. Okay? Any questions with the conjunction? Okay. We said the disjunction, A or B, relates to the union of 2 sets, okay? So we say the union of 2 sets is the set of all elements X such that X is in A. Okay, this shouldn't be the union sign. This should be this disjunction sign. The set of all elements such that it's in A or it's in B, okay? And notice the conjunction, it opens downwards just as the intersection symbol does, and the disjunction opens upwards just as the union symbol. Any questions with the disjunction? Okay, and we said the negation, read not A, relates to the complement of a set, right? So we say the complement of a set is a set of all elements that are not in that set, okay? So X such that it's not in A, okay? Any questions with the negation operation? Sounds good, okay? And so for example, let's say we have P at T means t is prime. Okay, so that's a proposition. And e at t means t is even. So that's another proposition. Both of these are propositions that depend on our variable t. What does, okay, I'm not going to read it out, but what does what we have written here, what does that mean? Any ideas? Yes. Okay, or more specifically, prime or not even. Okay, and we can sort of infer that if it's not even, it's odd. But what it says directly is, rather, it's true when t is prime or not even. Any questions with that? Cool. And so we also went over what an implication is and what a truth table is, okay? So we said P right arrow Q. There's supposed to be two branches to this arrow, which reads P implies Q. Says that if P is true, Q must be true, okay? And if P is false, it doesn't tell us anything about Q. So if P is false, we don't really know anything about Q. So for example, if we know today is Christmas, it must be December. But if it's not Christmas, it doesn't have to be December. Is that clear? Right? So here our proposition P is that it's Christmas. And the current month being December is Q, right? So we know that P implies Q when P is true, right? So if today is Christmas, we know the current month is December. But if today is not Christmas, we don't know that it's December. Or may not be December. Sound good? Cool. And we also finished off on introducing what a truth table was, right? And so what we use a truth table for is to prove logical equivalences, okay? So we say two logical expressions are equivalent when they have the same values upon all possible inputs, okay? So what we do is make one row for every combination of P and Q. So we have true and true, true and false, false and true, and false and false. And that's enumerating every possible combination of P being true or false and Q being true or false. Is that clear? So what if we had three propositions, P, Q, and R? How many rows would we have? 8, right? And that comes from 2 to the 3. And we'll talk more about that later in the course. So what we're doing here is showing that P implies Q is logically equivalent, and we use this equivalent sign, the triple equals equivalent, to not P or Q, okay? And how we do that is by enumerating all possible values of P and Q. So if P is true and Q is true, does P imply Q? Yes, because that's the definition of what P implies Q means. If P is true and Q is true, we know that that's exactly what an implication entails, right? If P is true and Q is false, does P imply Q? No, that's the only case where an implication is not true, right?
Why
Yeah.
is that?
Well, that's how we're defining an implication. We're saying that if P is true, Q must be true.
Okay, why is it when it's true and Q is false, why it's false?
Because if the way an implication works is that if P is true, we know that Q has to be true. But if, so right here where we have P is true but Q is false, that can't happen with an implication. So we say it's false.
But if you correlate this to the Christmas and the December,
Sure.
How does it apply there?
Oh, so you're saying what would the equivalent be in this example?
Yeah.
Does anyone have an answer to that question? So the question is, if P is today's date is Christmas and Q is the current date is December, what would be an explanation for the second row of this truth table right here? Yes?
Should we try to say for P, if today is Christmas, but then you say, and then it's not December?
Yeah.
Until you know it's Christmas.
Exactly. So if P is the proposition, it is Christmas, and Q is the proposition, is December. If it is Christmas, so P is true, but Q is false, meaning it's not December, that doesn't make sense, right? It can't be Christmas and also not December. Does that make sense?
So it's about make sense or not. This is how you judge.
Did you have something to
It
say?
implies that the arrow called again? The implication. Is
Yeah.
false.
Yeah, it's saying the implication
Yeah.
is false. It being Christmas does not mean that it's not December, right? If it's Christmas, we know it has to be December. So if we're saying it being Christmas implies it's not December, that's not correct. Because it being Christmas implies that it is December. Does that make sense? Okay, we'll go over more examples, okay? And feel free to ask again. Yes?
Like a kind of concept of media.
Okay.
Like cell in the truth table comes first one. So,
Okay.
then like that, P and Q were to be true, like implying Q
Yeah.
is the true value of this. I mean, I picture it as a true value.
Okay, it's whether or not the expression has, like, it's the value of the expression. Okay, so what was your name? Ishan. So the explanation that Ishan had, which I really like, is that each of these expressions has their own truth value. Okay? P implies Q has a value. It is either true or it's false. It's whether or not statement P implies statement Q. Okay? And the way we define P implies Q is that if P is true and Q is true, P does imply Q. But if P is true and Q is false, then the truth value of that statement is false. Okay, and the whole like it being Christmas implying that it's not December being false, those are just examples of what P and Q could be.
Basically, your P and Qs are what you plug into the two top things, like
Yeah.
P implies Q and not P implies Q. Those are going to be, like, your P and Q are going to be plugged into there, and that's what returns either true or false within that column.
Yeah. So like,
sort of
yeah.
You know when you did sign analysis for quadratics or like multi-polynomial graphs, whatever. Basically, you're just like your true and false for P and Q. That's going to be like, okay, if this is positive and this is positive, then will it give me a negative or a positive when I plug it in? This is essentially the same thing, but your equation is going to be the things on top of the columns.
Yeah. So what we're doing is plugging in true here and false here, and saying, if does a true value imply a false value? And the answer is no. So the value of this expression is false. Okay? Is everyone clear with that? Josh had a really good example on when we're looking at, I don't know, multiplying a positive integer and a negative integer. What is the value of that expression? Okay? And if you look at the definition of implication, if P is false, Q could be anything, right? If P is false, it says nothing about Q. Okay? So if P is false, it doesn't matter what Q is. These are all possible outputs. Okay? So that means if P is false, Q could be anything. We allow that. So though the value of P implies Q in those cases is true. Any questions with that? Okay. And so what we're doing with this truth table is showing that the operation not P or Q is logically equivalent to P implies Q. Okay? And we do that by plugging in the same combination. So we plug in true and true, plug in true and false, plug in false and true, and plug in false and false. And we see that we have the same values in each case, right? We have true and true, we have false and false, we have true and true, and we have true and true. Okay? So for all possible inputs, P implies Q and not P or Q give us the same outputs. Okay? That means these two expressions are the same thing. Okay? So we say P implies Q and not P or Q are logically equivalent. Any questions with that? Sounds good. Okay. So then the first new thing we want to introduce now is the idea of an exclusive OR. Okay? So our regular OR operation corresponds to true when A is true or B is true, and when both are, or when both are true. Right? So if we're talking about sets, I guess I can just write it on here. This element X is included in the union of two sets. Does everyone agree? Right? Even though it's only in set A. This element X is also included in the union, even though it's only in set B. Does everyone agree? And lastly, this element X is also included in the union of A and B, even though it's in both. Okay? So whether an element is in one or the other or both, it is included in the union. Similarly, with regular OR, if only one statement is true or the other statement is true or both are true, it's included, the output is true. Any questions with that? So this is our regular OR. So what we want to do is define this operation XOR, which the symbol in LaTeX is O plus. That is true only when exactly one of A and B is true. Okay? So it's true when only A is true. It's true when only B is true. But it's false when they're both true. Is this clear? So let's write out what the table for this would look like. A, B, and A plus B. Okay. When A is true and B is true, what is A XOR B? True or false? False, right? So the way we're defining it is such that if both values are true, it is false. Okay? What about when A is true and B is false? True, right? What about when A is false and B is true? True. And what about when they're both false? False. Okay? So notice, it happens to be the case that A XOR B is true when A and B are different. Is that clear? When we have true and false or false and true, the output is true. But when they're both true or they're both false, the output is false. Any questions with that? Okay? And so now our job will be to try and figure out a logical expression that is equivalent to A or B. Okay? So what I'll do is give you 2 minutes to work with the people around you and try and come up with some combination of nots, ors, or ands that is equivalent to A XOR B. Is everyone clear on what the problem is? Okay, cool. So I'll give you 2 minutes and let's work on that. Okay, in the interest of time, we want to move on. But how many people think they have some sort of equivalent statement to A XOR B? 3 people. Okay. Does someone, or 4 people? Does someone want to, 5 people? Does someone want to volunteer their proposed solution? Sure.
I think A or B.
Okay.
And not A and not B.
Okay, so what you're saying is that it looks something like, I don't want to go to the next slide because there's the answer. You say A or B and not A and not B. Okay. How many people had something else? Do you have a proposed solution?
I had not A and B
Okay.
and A.
Okay.
And it's like,
So it's very similar, but instead you have A or B and not A and B. Right? Okay? Yes, up here.
We've had not A and B or A and
Can you repeat that?
parenthesis not A
Yeah.
and B or parenthesis A.
Okay. Cool. Any other ideas? Yes.
A ordered was not B. Sorry, A ending was not B.
And not B.
Correct.
Okay.
And then or
Okay.
not A ended with B.
That's exactly what's right here.
Oh.
Cool. So it seems like we had 3 solutions. Okay. Here we have what the solution is. Okay? But it turns out that there's not just only one solution to this. Okay? So the claim that I have is that it's equal to or equivalent to A or B and not A and B. Okay? It happens to be the case that, that's exactly what this is. But it happens to be the same as the bottom expression I have as well. Okay? Unfortunately, this is not true, so I want to just erase that. Maybe. Sorry. But we have that it's equal to A or B and not A and B. Okay? So it's true when either one of them is true, but not true when both of them are true. And that's sort of just a direct translation of what it means in English. Okay? And here we have a truth table showing why this is the case. So in this third column, we just copied and pasted what we had right here, right? False, true, true, false. But in this fourth column, we reevaluate this expression with the values of A and B on the corresponding row, right? So when A is true, B is true, the A or B is equal to true. Does everyone agree? Right? If A is true and B is true, A or B is true. And not, well, if A is true and B is true, A and B is also true. Agreed? So that means we have true and not true. Well, that's false, because that's the same as true and false. Okay? As another example, if we have A is true and B is false, we have true or false. Well, that's equal to true. And not, well, we have true and false again. So true and false. So what is the first bracket equal to? True or false? That's true. And not, what is true and false equal to? False. So we have that this is true and true, which is true. Okay, so that's sort of how we would evaluate these expressions, okay? And so we show that A, X or B is logically equivalent to this expression we have here. Any questions with that? Yes?
Is it the shortest expression, or do you think it's shorter?
This is as short as it gets. Yeah. Because you sort of have to encapsulate all the conditions. One of them is true, but not both of them are true. And this is a literal English translation of exactly what I just said. Good question. Sound good? Cool. So we can go through this relatively quickly because a lot of it was on your homework. We have two extensions of the implication P implies Q. Okay? We have the contrapositive not P implies not Q, and we have the converse Q implies P. Okay, so let's take a look at both of these in a little more detail. So the first, the contrapositive not Q implies not P, is actually logically equivalent to the implication P implies Q itself. Okay, and what we do is recall the formula P implies Q is logically equivalent to not P or Q. Okay, we apply that formula right here. Okay, so we have not Q implies not P. We plug that into the relation P implies Q is equivalent to not P or Q. So we take the negation of the first item, right? So the negation of not Q is just Q because it's like negative X, which is the same as X, right? Or the second item, right? Because in an implication, P implies Q, take the negation of the first item and OR it with the second item. Okay? So we have not Q or not P. Well, not Q is the same as Q, so we have Q or not P, which is the same as not P or Q, which gives us P implies Q. So is everyone clear on why the contrapositive of an implication is the same thing as the implication itself? Any questions with that? Okay, so as we've sort of written out here, not Q implies not P is the exact same thing as P implies Q. Okay, and so what's the use case of the contrapositive? Well, we'll see when we talk about proof techniques in lecture this Wednesday. Sometimes when we want to show that one statement implies another statement, it might be easier to show it in terms of the contrapositive. And since both statements are equal, we can prove some statement either way, either by doing a direct implication or a direct proof, or by doing a proof by contraposition. Okay, so that's the reason we care about the contrapositive, even though it's equivalent to the proof itself, or to the statement itself. Okay, for example, the statement, if it is sunny outside, I will wear my sunglasses. The contrapositive of that is, if I don't wear my sunglasses, right? So let's say this is P, we'll wear my sunglasses is Q. So if I don't wear my sunglasses, that's not Q. It is not sunny outside. That is not P. So that's how we would convert a statement into its contrapositive. Any questions with that? And that was sort of on your homework. It's okay. Like the idea was that you read the textbook and sort of attempted it. But if you had trouble with that, that's okay. That's what we'll talk about in discussion. Any questions with that? Okay. the converse, okay? So a regular implication, P implies Q. The converse is Q implies P, okay? And clearly, the converse of an implication is not the exact same thing as the implication itself. Whereas the contrapositive was logically equivalent to the original implication, the converse is not logically equivalent, okay? Not equivalent. Unlike the contrapositive. Okay, so for example, if today is Christmas, it implies the current month is December. Okay, going back to this example. But if it's December, it doesn't imply that it's Christmas. It could be any other day. Is that clear? Right? So if P is today's being Christmas and Q is the current month is December, we have that P implies Q, but Q does not necessarily imply P. It does not imply P, right? If today's December, it doesn't imply that today's Christmas. Sound good? Cool. And I'm going through this relatively quickly, but again, we'll have more opportunities to work with this. Let me get to this guy. Okay? So one of the last things I want to cover is the idea of if and only if. And we've seen this a lot starting from lecture in day one. Right? We have one thing is true, if and only if, this other thing is true. Okay? And essentially, if and only if is a fancy way of saying that two statements mean the same thing, i.e. that two statements are equivalent. Okay? And there should be a triple equal signs there, right? And what if and only if means is that A is true only when B is true, and B is true only when A is true. Is that clear? So what if and only if really looks like is the same as A implies B and B implies A. Is that clear? And so what we have is that this ends up being equal to A is equal to B. So, okay, going back to this Christmas, December idea, it is Christmas if and only if it is December 25th. That's our if and only if statement, right? So any statement that says if and only if, we can break it down into one direction and the other, right? So if we say A if and only if B, we can show one, that A implies B, and two, that B implies A. And together, they show that A and B both imply each other. Is that okay? Yes?
So the difference between this and the arrow,
Yeah.
the arrow one is that B imply A, but the other
It's only one direction.
Okay.
Yeah, exactly. So notice how here we have arrows both ways. Okay? So with the regular implication A implies B, we just have that A implies B. B doesn't necessarily say anything about A. But by adding this double arrow, we're saying that A implies B and B implies A. Is that clear? And that's sort of reflected up here. A implies B and B implies A. Sounds good? Okay? So for example, if it is Christmas, if and only if, and sometimes if and only if is written as IFF. Okay? So if you've seen that before, that's what this means. It decomposes into the two individual statements. It is Christmas if it is December 25th, right? So that's A implies B. And it also decomposes into it is December 25th if it is Christmas. Is that clear? So if it's Christmas, I guess that can be our statement A. And if it is December 25th, that can be our statement B. Here we have A implies B, and here we have B implies A. Okay? So this is all just a bunch of fancy talk for saying that Christmas and December 25th are the same thing. Yes?
So what's
They're sort of used in different contexts. So sometimes, like, I don't know, for example, back here, maybe here, we use the equivalent sign to show that these two things mean the same thing, right? These two statements are logically equivalent. Okay? And it was almost like, I don't know, think back to trig identities or something, just rewriting one thing in terms of another, okay? Whereas, now when we talk about if and only if, it's more of saying that two mathematical properties are equivalent, right? And to do that, we will show that one implies the other, and the other implies the first one. Okay, so it has its roots in proof techniques, right? So to show that two expressions are equivalent, we'll end up having to show that one implies the other and the other implies the first. Okay? Is that clear? So a lot of this will make a lot more sense when we talk about proof techniques on Wednesday. Sound good? Okay, so that's a good question. Why do we care about this idea of if and only if we could just say two things are equivalent? Well, it'll be important when we talk about proofs. Sounds good? Okay. So here we have the truth table comparing A if and only if B and the expression we had before. A implies B and B implies A. And we see that they're equivalent. Okay? Sounds good. And these slides will be posted. Okay, this is the last thing I wanted to go over before we take attendance and go into discussion mode, okay? So the last two things we sort of need to talk about are these ideas of existential quantifiers. Okay, so there's sort of the glue that helps us put together conjunctions, negations, disjunctions, implications, contrapositives, converse. It allows us to convert sentences that we say in English to precise statements in math, okay? So we have two, the for all symbol, which looks like an upside down A, and the existential symbol, or the there exists symbol, which looks like a backwards E. I don't know who came up with these, but whatever. Okay, and we've seen these before, right? So I use the definition, like when we define when a function is surjective, we said that a function is surjective when for all B and B, there exists an A in A, right? So we've seen this before, but we didn't formally define it. Now we're formally defining it. Okay? So for example, suppose E of x means that x is even and U of x means that x is odd. What does the first statement mean and what does the second statement mean? Can anyone tell me what the first statement means? Yes.
For every x in the natural numbers,
Yep.
X is even or x is odd.
Good. So the first one says, for all naturals x, x is even or x is odd. Does that happen to be a true statement?
Yeah.
It is, okay? But there's no requirement that it needs to be, right? And as you'll see, the second statement is not true. So the first one is true. Good. Okay? What about the second statement? What does that say? Yes?
For all naturals, x.
Okay, good. So the second one is saying for all, you know what, let me write it in a more, what's the word, colloquial way. All natural numbers are both even and odd. Is that true? No, right? So these are just the building blocks in creating statements, okay? The statements themselves can be true or false, right? But we need these ideas of for all and there exists to create these statements. Okay? And notice how in the second one I wrote it in the more English way, right? The first one I said, for all naturals x, x is even or x is odd, right? Nobody would say that, right? You'd say all natural numbers are either odd or even. I sort of wrote the second proposition, or the second statement in that way, right? All natural numbers are both even and odd. And that's the direct translation of what the second statement says. Okay? It happens to be false for all inputs x. But that's sort of the conversion. Any questions? Cool. Very last slide. We want to talk about this idea of De Morgan's laws, okay? So we've seen De Morgan's laws 2 or 3 times now. So we saw it for sets, right? And this was something we had to sort of show in the first homework. We also saw it for conjunctions and disjunctions, I believe in the textbook, but we didn't talk about it in lecture, and we're not going to because it gets a little complicated. But we also see it for existential quantifiers, okay? So what De Morgan's laws do is they allow us to look at the effects of the negation operation on different existential quantifiers, okay? So for one, we say that the negation of for all x, that P of x is true, is equivalent to there exists an x that P of x is not true. Okay? And the second statement says that if it is not the case that there exists an x that p of x is true, then for all x, p of x is false. Okay? So for example, if it's not true that everyone in this class is a sophomore, then there has to exist one person that's not a sophomore. Is that true? Or sorry, is that clear? Right? This is just an encapsulation of that idea. If something is not true about an entire population, then there has to exist one element or one person in the population for which it's not true. Okay? Just like if it's not true that all numbers are prime, there has to be one number that's not prime. At least one number that's not prime. Okay? And that's sort of what De Morgan's law tells us. Okay? Similarly, if it's not true that there exists a prime number, then every number is not prime. Okay? Similarly, if there's not a single sophomore in this room, then nobody in this room is a sophomore. Is that clear? And so those two statements are equivalent, but we're just writing it formally with the for all and there exists notation. Is that clear? Cool. And so we'll have a lot more practice with these ideas in the homework, or so you already had that sort of practice, but we're about to go over those questions now. So any questions with anything that we just covered? Okay? And so the video for this will be up later tonight, because now it's much easier that I recorded this. I can sort of just post it. Feel free to post clarifications on Piazza. But for now, take 5 minutes, or maybe less than 5 minutes, to do attendance, and we'll get into discussion. Okay? Cool.